Okay, there's two big bits of news, two things that should be at the front of your mind. The first one is I should have made this decision earlier. It didn't really occur to me until earlier today, but the next lab that I have could use a couple more lectures to really be that useful. And so we're not doing any labs this week. Okay, so no lab today, no lab Wednesday. I will be there during the lab period today. So if you want to come in and I can give you problems to work on or answer questions or whatever, that's open to everybody. So you don't have to come to lab today, but you're welcome to come and ask questions. And if you want me to make up problems, I can make up problems and that kind of thing. Okay. And then the second thing is, the reason you might want to come and ask questions is that exam 1 is on Wednesday. And the topics for exam 1 are everything up through, so everything we've done so far up through 1D particle kinematics. And so today, question, yeah?
When you say Wednesday, do you mean Wednesday of this week or Wednesday of next week?
It's Wednesday of this week.
Okay.
Yep, 2 days. That's right. So today I'm just planning to write some problems up here, give you time to work on it. I'll go through it and you can, hopefully sort of iron out any issues that you're having with the problems, the kind of stuff that's going to be on the test. The test is all going to be problem solving like those assignment problems that you've been getting. So if you can go through all those assignment problems and you know how to do them all and you could explain to someone who's confused about it why you did this and this, then you'll do great on the exam. Okay, so before I get into some new problems, does anyone have any homework problems you'd like to see? I'd be happy to go through any homework problems that have been confusing. Okay, well, let's start out with a couple of position versus time type problems. So let's say that this distance is 2 centimeters. This distance is 5 centimeters. And this distance is 1 centimeter. And let's name these points A, B, C, and D. And let's say an object starts at B, goes to A in 1 second, then goes to C in 3 more seconds, then back to B in 2 seconds, and then finally to D in 3 seconds. Okay, and so we're going to start with the 0 position at C and 0, and the positive direction to the right. And then time equals 0 is going to be at the start of the motion. And we want to draw a position versus time graph. Yes?
Did you say 1 meter, or is that supposed to be?
That's supposed to be a centimeter, you're right. Thanks. Okay, so take a second and first, why don't you start by first just drawing sort of on this number line thing, a sketch of what the motion looks like and show the times of the different instants. I'll give you a minute or two to do that, and then we'll go on to the next part, okay? So see if you can just sort of squiggle out it's where it starts, where it goes to, what the times are when it arrives at those different points that are mentioned. Okay, are you with me on that? Okay, so this first thing, so the motion starts at B, so I'm gonna just start here, goes to A in 1 second. So this takes 1 second. Then from A, it goes to C in 3 seconds. So this part takes 3 seconds. And then it goes back to B in 2 seconds. And then it goes all the way to D in 3 seconds. So since you know these times, and times just add up as you go, and time equals 0 when the motion starts, we know that this is going to be at 0 seconds. 1 second later, the stopwatch is going to say 1 second. 3 seconds later, it's going to say 4 seconds. 2 seconds later, it's going to say 6 seconds. And then 3 seconds later, it'll say 9. Okay? Any questions about that? All right, so now label the position in the positive direction and use that to come up with the positions of A, B, C, and D. Okay? So take a couple minutes to do that. Just see if you can figure out the positions at A, B, C, and D. The 0 position is C. What's going on here? Okay, so 0 position is C. The positive direction is to the right. So negative is to the left. So first of all, if you start at 0 and go 1 centimeter in the positive direction, what position are you at D? Yeah, that's positive 1 centimeter. And if you start at 0 and go 5 centimeters in the negative direction, what's B? Yep, negative 5. And if you start at negative 5 and go 2 centimeters in the negative direction, what are you at A? Yep, negative 7. Okay, so now from here, I would recommend writing out a table, but now take the last step and go through, if you're doing a table, do the table, and then draw the position versus time graph based on those values, okay? So based on what we have written so far, I can write out a table like this. at that first instant of the motion, you can see the motion starts at B at a time of 0 seconds. What's the position corresponding to 0 seconds? Yep. And the next thing we know is the time 1 second. What's the position at 1 second? Yep. The next one is 4 seconds. And what's the position there? Yep, that's at 0. And then 6 seconds. What's the position? Yep. And then last is 9 seconds. And what's the position? 1. Yep. Anybody have any questions about coming up with those? And so now, let's see, what are the values that we need? So time is on the horizontal, position is on the vertical. We need -5 and -7. And then +1. And the times are 0, 1 second, 4 seconds, 6 seconds, and 9 seconds. And the last step is just plotting points. So the first point is 0, -5. Then 1, -7. Then 4, 0. Then 6, -5. And then 9, 1. And so all together it looks something like this. In real life, these would be curved somehow. You'd have, and those curves, remember, tell you what the acceleration is. So, you know, it really would be something like this. And those curves would indicate when it's speeding up and slowing down. But for questions like this, you could just draw them as straight lines. Okay, let's do one more with this. So let's say that this time the 0 position is at B. And the positive direction is left. And time equals 0 is 2 seconds before the motion starts. So when the motion starts, the time is going to be 2 seconds. And again, you just want to draw a position versus time graph. Okay, so oh, and I left off the motion. Well, okay, so the motion is going to be the same. This time, instead of doing it in steps, just go all the way through and see if you can come up with a position versus time graph. And when you're done, I'll go through it. This one. So the motion starts at B, goes to A in 1 second, to C to B to D. So the motion is still the same. This is 1 second, 3 seconds, 2 seconds, and 3 seconds. And for part B, the motion starts 2 seconds before the stopwatch starts 2 seconds before the motion. So when the motion starts, the stopwatch is going to say 2 seconds. 2 plus 1, this instant will be 3. 3 plus 3, this one will be 6. 6 plus 2, this one will be 8. 8 plus 3, the last one will be 11 seconds. Any questions about that? Anybody get anything different and want an explanation on that? And now for the positions, 0 position is at B. And the positive is this way, which means the other way is negative. If you're at 0 and you go 2 centimeters in the positive direction, you're at positive 2 centimeters. If you're at 0 and you go 5 centimeters in the negative direction, you're at negative 5. And if you're at negative 5 and you go another 1 in the negative direction, you're at negative 6. And so now I'm going to draw out a table. And we have 1, 2, 3, 4, 5 instants that we care about. The first one is at time 2 seconds and position 0. The second is at time 3 seconds and position 2 centimeters. The third one is at time 6 seconds and position negative 5 centimeters. The fourth one is at 8 seconds and back at position 0. And the fifth one is at 11 seconds and position negative 6 centimeters. And so this time, the positions we care about are negative 5 and negative 6. And the times we care about, oh, and there's one more actually, positive 2. And the times are 2 seconds, 3 seconds, 6 seconds, 8 seconds, and 11 seconds. And if I plot out these pairs, we have 2, 0. 3, positive 2. 6, negative 5. 8, 0. And 11, negative 6. Anybody have any questions about that? Okay. Now let's go on to a couple example problems with the constant acceleration equations. So let's say we send a ball rolling up a ramp, and let's say that the ball reaches its highest point a distance of 3 meters from this starting point, and it takes that's a really weird S. It takes 2 seconds to reach the highest point three meters away. And we want to calculate first, what's the acceleration? Second, actually, we do need to know what the speed is, I think, here. So let's say that its starting speed is 3 meters per second. Okay, so what's the acceleration? And after the ball rolls past its starting point, what's its velocity 2 meters to the left of where it started? Okay, so what's going to happen is the ball is going to roll up, slow down, get to this as the highest point. Then it'll start rolling back down the ramp and speeding up. And when it gets past where it started here, where this distance is 2 meters, what's its velocity going to be? Okay, so to start, let's all just get on the same page with this first. We have to make those 4 choices, a 0 position and a positive direction, and then an instant for time equals 0 and an instant for time final. So for part A, let's make all those choices together. What do you want to choose as 0 position? There's no wrong answer for 0 position or positive direction. I think a lot of people would probably just choose the 0 position to be where it starts. So we'll call position equals 0 the location where this motion starts. And the positive direction, let's call that up the ramp. And now the times, these are the ones that are important. If you get these wrong, you usually can't do the problem at all. So time equals 0. What do you want to call the instant for time equals 0? Yeah, again, that's probably the best one. And then what do you want to choose the instant time final? So for part B, that is going to have to be time final when it reaches that point. But what you would see if you try to do part A with that is that we don't have enough information yet. So for this one, because we have information when the motion starts, And because we have information when it gets to that highest point, because notice the information we have when it gets to the highest point is we know it's 3 meters away, so we can get a position out of that. And we know that it's come to rest before it starts rolling back down, you know? So we know the velocity is going to be 0 there. And so we're going to choose our time final to be the instant that it reaches the highest point. Okay, so now take a few minutes and see if you can work through this problem given those choices, okay? Just for part A. We'll do part B after this. Part A. We made these 4 choices. The next step is to list out what variables we know and what variable we're trying to find. And I'm just going to go in order all through the variables that show up in the constant acceleration equations. TF, A, PI, PF, VI, VF. So TF, we don't know how long it takes to get from the starting point to the highest point. Oh, yes, we do. It takes 2 seconds. So TF is 2 seconds. The acceleration is what we're trying to calculate. P initial, the position at time equals 0, is 0. P final is the position up here at the highest point. That's 3 meters in the positive direction from 0, so PF is positive 3. V initial is 3 meters per second. And it's moving in the positive direction, so that's positive. And V final, since at time final it comes to rest here, that's equal to 0. And so we need an equation that that includes A in it, and everything else in it is known. So let's try this equation. You can see A is in it, VF is known, VI is known, TF is known, so this one will work. Did anyone use a different equation? There's another one that would work too. And actually, you know, the thing is I gave 1 too many bits of information. So if you use this equation, that's perfectly fine. But most likely you'll get a different answer. That's my mistake in making this problem, so sorry about that. Either one of these two will work, but I'm going to use this one. Okay. I'm going to use this one because it's the simplest. If it works, always use it. Okay, so V final is 0. That's equal to 3 plus 2A. And so 2A is equal to negative 3. And so A is equal to negative 1.5 meters per second squared. And so what I should have done was not give this distance of 3 meters here, and then it would have worked either way. Any questions about that? Okay, so now that you have this acceleration, we want to go on to part B and calculate the velocity when it gets to this point here, okay? And you're going to use this acceleration that we just calculated. I want you to notice that in part B, you're going to have to choose a new time final because we're looking for information at a new instant. And so if you kept the same time final, there'd be no way to calculate what's going on at this new instant. Okay, so your new time final is going to have to be when the ball reaches this second spot. Okay, so take a few minutes and see if you can do part B. So let's list out what we know and what we want. We're given that it takes 2.5 seconds to hit the ground, so time final is 2.5 seconds. It's a free fall problem, so acceleration is down at 9.81. To us, down is negative. P initial is positive 1 meter. P final is 0. We're trying to calculate the initial velocity, and we don't know the final velocity. So the equation that works with these should be this one. So enter in the value. 0 is equal to 1 plus 2.5 VI minus 4.905 times 2.5 squared. Subtract all the numbers from both sides and you get that 29.66 is equal to 2.5 VI. Divide both sides by 2.5 and you get that VI is equal to 11.86 meters per second. Does it make sense that that value came out positive? Yeah, because at the instant it's launched, it's moving up, which we called positive. Okay, now for part B, now we're trying to figure out the highest point in the flight. Is there any reason that we need to change any of our 4 choices? In this problem, there is one we have to change. We're trying to calculate something at the highest point. And so one of our 2 instants has to be the instant it reaches the highest point. Okay, so I'm going to change my time final to be the instant it reaches the highest point. The other 3 things can stay the same. So take a few minutes and see if you can calculate the highest point in the flight. But okay, so we have this new choice of time final. We don't know time final. We don't know what the stopwatch says. So I'm just going to leave that off. Acceleration is still negative 9.81. P initial is still positive 1 meter. We're trying to find P final. That's the highest point. V initial we calculated in the last part. This is 11.86. And do we know V final?
0.
0, yep. So anytime you're looking for the highest point, you're going to use the fact that The velocity at the highest point is 0. The equation we can use here is 2a times the quantity pf minus pi is equal to vf squared minus vi squared. So 2 times negative 9.81 times the quantity pf minus 1 is equal to 0 squared minus 11.86 squared. So negative 19.62 times the quantity pf minus 1 is equal to negative 140.66. Divide both sides by negative 19.62. And you get pf minus 1 is equal to 7.17. Add 1 to both sides, and the highest height it reaches is 8.17 meters. Right around 25 feet. And then the last part, I asked what the velocity is just before it hits the ground, or you can think of it as the instant that the object passes through the height of the ground, if you imagine the ground isn't there. So this time we have to choose our t final to be what it was again in part A. So it's the instant that it reaches the ground level. Well, originally we were given the amount of time it takes to reach the ground level, so now we know TF again is 2.5 seconds. Acceleration is negative 9.81. P initial is 1 meter. P final is 0. V initial is negative 11.86. And we're looking for V final. And now that we've done all these parts, we know a lot of variables, and that means probably more than one equation will work. But if you can ever use this equation, use it, because it's simpler and you don't have to think about directions because nothing's squared. So let's use VF is equal to VI plus ATF. So VF is equal to, VI, this should have been positive, sorry. It's on the way up at the instant that it's launched. So VF is equal to 11.86 plus 2.5 times negative 9.81. And so VF is equal to negative 12.67 meters per second. Does it make sense that that final velocity is negative? Yeah, because it's on the way down. Now here's another question. Does it make sense that that's a little bit bigger in absolute value than the starting velocity? Yes, because once it reaches that starting height again, 1 meter off the ground, we know it's going to be going exactly negative 11.86. And gravity is just going to make it speed up a little more as it falls that extra meter. Okay? Any questions? All right, well, yeah, if you have any things you want to talk about for the test or want me to come up with problems, come over to lab. And otherwise, I'll see you on Wednesday.